welcome to your science review with Mr. Blades. Now, I understand that almost nobody will catch this because I didn't mention it in class, but there it is. So anyway, let's see. Okay, so I've got all this extra space. Okay, so the intent right now is to just do 3 problems back to back to back and be out of here in like a quick 20. So I'm going to talk as much as I can and show as much math as I can. So let's go ahead and get started. So battery, positive, negative part of the battery, resistor, resistor, resistor. Okay, now what kind of circuit is that? That is very clearly a series circuit. And let's go ahead and number our resistors. Now, I told you that I want you guys to do your math in this way with the whole table thing. R, okay, and that's what we're going to do. Now, I don't have enough space to write, volts, ohms, and amps, but just assume that they're there. Okay, there we go. Now, just for the sake, let's go ahead and say we have 18 volts of total voltage, and that we have, let's say, 4, 6, and 8. 4, 6, and 8 for our resistances. Okay, Brian, what direction does the energy flow? Just like we said before, it flows in the direction from positive to negative. So it will flow that way. And of course, we remember that this is just convention. It does not actually flow in that direction. We just say it does. Okay, it actually flows in the opposite direction. But like I pointed out, the correct answer on the quiz is that it flows from positive to negative. Okay, so like we said, this is a series circuit. So let's write down the things that we know about a series circuit. First of all, I1 equals I2 equals I3, etc. And our total resistance is R1 plus R2 plus R3, etc. And then last, that our voltages add up to the total as well. So V1 plus V2 plus V3, however many we have in that order. Okay, so first things first, we want to shrink this whole thing down as though it were just one, resistor, like this. We want to imagine this as though it were that. Okay, so we need to combine all of our resistances and see how it works out. So we're going to go ahead and use this equation right here because it talks about total resistance in a series circuit. So boom, there we go. So our R total is equal to 4 plus 6 plus 8 ohms, or 4 plus 6 is 10, 18 ohms. Okay, there we go. Now we can use our Ohm's law. V equals IR. We know our R, we know our V, so I is equal to V divided by R, or 18 divided by 18, or 1 amp. Okay. Now, this property of series circuits tells us that the current is the same everywhere in this circuit. Now that we have imagined it as 1, we're moving back to imagining it as 3. And as we already pointed out, our current is the same everywhere in a series circuit. So 1, 1, 1. All of those currents are the same. And now we can apply our Ohm's law again. V equals IR. We know R, we know I. This times that equals V, or 4, 6, and 8. And as we can see, 4 plus 6 plus 8 equals 18, which corresponds to our identity down here. and boom, there we go. Fully filled out series circuit. Okay, now let's go ahead and get ready to do another one. 1, 2, 3, and total. Okay, there we go. And let's go ahead. Okay, so 1, 2, and 3. And let's go ahead again and say, let's just pick 20 volts. So 20, and let's pick 15, 4, and 3. Why did I pick those? I don't know. Anyway, so let's go ahead and figure out what kind of circuit is this. Well, by now you should recognize it as parallel. This is a parallel configuration because it branches from a single point. It branches from right there. Okay, now some of the things that are true about parallel circuits is that instead of current being the same everywhere as it is in a series circuit, voltage is the same everywhere. So V1 equals V2 equals V3, dot, dot, dot. Again, keeping up with the inverse idea, our current actually adds up this time instead of our voltages. And lastly, we remember that our resistance is calculated with this weird looking thing. 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3, dot, 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 as many of those as you have. Now, before you calculate the total resistance, though, be sure to take the reciprocal of this guy, because if you forget to, then you just have a wrong answer. Okay, so first things first, we want to imagine this as a single resistor, okay? That's all we want to do. So we need to get started with this whole 1 over RT thing. So we have 1 over RT is equal to 1 over 15 plus 1 over 4 plus 1 over 3. And that gives us 1. And that gives us 0.65, pardon my handwriting. And when we take the reciprocal of both sides, 1 divided by that answer, we end up with a total resistance of 1.538. 0.538. Mr. Blades, how do I know how many decimal places to go? Well, there's not really a rule because I don't care about significant figures, but I do tend to go 2 or 3 until I don't have to round anymore. But there we go. So now we have our total voltage and our total current, our total resistance. And so now we can figure out our total current. And again, we just apply V or I equals V over R, or 20 equals 1, or I equals 20 divided by 1.538. Yeah. Well, ain't that nifty? It comes out to exactly 13. Well, there we go. 13. Okay, now we have to figure things out as by applying our identities just as we had before. Now, our voltage is the same everywhere in a parallel circuit, and this is just a plain old parallel circuit with nothing crazy going on. So our voltage will be the same in every single branch. So we can just apply 20, 20, 20. Okay? And because of this guy right here, we know that the sum of I1, I2, and I3 should equal 13. So let's go ahead and see if that's how that works out. Okay? So our I is going to be V divided by R, or 20 divided by 15. So 1 and 1/3. This one would be 20 divided by 4, or 5. And so I'm expecting to see 6 2/3 for this guy. And this last one is 20 divided by 3, or 6 2/3. 1 1 1/3 plus 6 2/3 is 8, plus 5 is 13. So, boom, there we go. We applied Ohm's law, used our identities for a parallel circuit, and there we go. Okay, that is a parallel circuit. If you have questions, this is the time to ask me, because I'm about to do my last problem and then I will be out. Okay. Boom. Okay. And lastly, a combination circuit. Can you see that? Okay, good. Okay, my drawing, oh well. But 1, 2, 3, 4, 5, 6 resistors. Okay, and so we have a, let's say, 20-volt battery connected to a parallel component that is in series with another piece along this parallel. Actually, hold on a second. We have a parallel section that consists of 2 resistors in series. That series part is in parallel with 1 resistor. This parallel component is then in series with 3 other resistors. So let's go ahead and make our table. V, Y, R. And 1, 2, 3, 4, 5, 6, and total. Okay, so let's go ahead and say 20 volts, and then 1,000, 5, 14, 16, 20, and 50. I mean, well, okay, Sean, but in the near future, like nearer than right now, you can ask for help right now. All right, so we've already talked about the identities for parallel and series. Now, what kind of circuit do we have here? Well, there is parallel elements and series elements. So we know that we have a combination circuit, regardless of how bad my handwriting is. Okay, so we're going to use all of our identities regarding the circuits that we have to solve these problems, okay? But first, we still want to look at this whole thing as though it were one resistor. And that's going to require combining these 3 together as one, and then these 3 together as one, and then combining those 2 together. But let's go ahead and get started. Let's start with the hard part, just because, and talk about this part up here. 1 and 2. 1 and 2 are in series with each other. This part is in series with each other. And we remember that our total resistance for any section in series is just add them together. So R1 plus R2, or 1,000 plus 5. 1,000 plus 5. Okay, so 1,005. I'm going to write kind of small because I've got a lot of math to do. 1,005. And now we need to combine these two, which we're imagining is 1, with this one right here, which is in parallel. So our 1 over R123 is equal to 1 over 1005 plus 1 over 14. Let's go ahead and calculate that out. And that gives us 0.0724. And 1 divided by that is 13.8. Now, even though this is really big, the outcome of a parallel resistor, the parallel total resistance, has to be smaller than either of those resistors. So no matter how big this is, this still needs to be less than 14. Okay, so now we can imagine this as one big resistor at 13.8 ohms. And now we have a resistor here, one imaginary resistor, and that's in series with 4, 5, 6, and 6. So our total R is equal to R123 plus R4 plus R5 plus R6, which equals 13.8 plus 16 plus 20 plus 50, or plus 16 plus 20 plus 50, or 99.81. 99.81. Okay, so 99.81. Okay, now, just like we did before, now we can figure out our current using Ohm's law. I total equals V total divided by R total. So 20 divided by 99.81, or 0.2. 0.2 amps. Okay, now because we're imagining this as a resistor in series and the other 3 of these are in series, we know, just like we did before, that the current is the same everywhere. So the current for 4, 5, and 6 is 0.2. And that allows us the opportunity to calculate their voltages. Okay, so 0.2 times 16 is equal to 3.21. Times 20 is 4.01. And this is 10.01. That's just how that's working out with the rounding error. Anyway, so boom, there we go. Now, we remember that the voltage through this resistor must be whatever's left over. Okay, and that the current through here that goes in here and then comes out here must also be 0.2. Okay, must add up to 0.2. Now, whatever voltage is left over from this 20 after being used up by 4, 5, and 6 is whatever voltage occurs in our parallel circuit there. So we have 3.21 plus 4.01 plus 10, and 20 minus whatever that is whatever our voltage is left. Now, these two resistors up here will split whatever voltage is goes through that top branch, but this one down here only does its own. So our V for 1, 2, 3 is equal to our total V minus V for 4 minus V for 5 minus V for 6. And if you add those up, again, I'm trying to save some space, we end up with 2.78 volts of electricity that are left. Okay, so as far as resistance always be given, not necessarily, but we will always give you enough information to solve the problem. You might have to do some of these backwards instead of the direction we're giving you, but there will always be enough information for you to solve. Okay, so we have 2.78 volts, and now we can solve for how much current is through that section. So 2.78 divided by 14, I equals V over R. So 2.78 divided by 14 equals 0.199. See, this is the problem with making up problems on the spot. Okay, so what that means is there is very little current that flows through that side, through the top part. Actually, so much so that our current left over, so I of 1, 2 is equal to the total current through this piece, this parallel piece, minus the part that goes just through number 3 at the bottom there. So 0.2 minus 0.199, or 0.0014. There we go. And I can do that because these two pieces are in series, and that allows me to know that the current is going to be the same through both of those resistors. And then lastly, I just multiply I and R to get my V. So that times 1,000 equals 1.43, and times 14, and then this last bit, oh, I did that wrong. Divided by 14 times 5. What did I do wrong? Oh, okay. Oh, hold on a second. Hold on a second. Let me figure that out. 2.78 divided by 14 equals that. And 0.2 goes in. Okay. Did I? Hang on a second. Okay, so this isn't coming out right, which means hold on one second. Let's look at this. Okay, so let me check my math. I might have gone too fast. So there's a problem here. Okay, so 1 divided by 1005 plus 1 divided by 14, 1 and then okay, so 0.724, 1 divided by 0.0724, 13.8, 16, 20, and 50. 16 plus 20 plus 50 plus 13.8, so 99.8. Boom, there we go. So 20 divided by 99.8. Okay, so 0.2. And those be the same. So 0.2 times 16, 3.2. 20 times 0.2. And 50 times 0.2. So 3.2 plus 4 plus 10. So 220 minus 17.2. So 2.8. So this voltage plus that voltage should equal 2.78. So divided by 14, so that much voltage goes through there. So 0.2. So essentially nothing goes through there. So 0.114. So 0.00414 times 1,000 and 5. Okay, well, all my math is right. It's just this right here, the fact that I picked 1,000 because I was trying to be funny, screws it up. But either way, there's one other way to find it. So since I checked my math, we're going to go ahead and find it. Now, we have 2.78 volts that must be going through here. So V12 equals 2.78 volts. Now, the resistance here is 1,000. The resistance here is 5. So if we apply V1 equals I1 R1 and then divide it by V2 equals I2 R2, because both those things must be true, we end up canceling those out because they're the same, but we end up with V1 over V2 equals 1,000 divided by 5. So the voltage eaten up by number 1 will be 200 times bigger than over here. That's what's messing up our math, is that it's so big. But we also know that that V1 plus V2 equals 2.78. Okay, so we can just go ahead and solve it that way. But so we end up with V1 equals, let me just make sure, 1,000 divided by 5, so 200. V1 equals 200 V2. So we can put this in place of V1 down here, and we end up with 200 V2 plus V2 equals 2.78, or 201 V2 equals 2.78. So 2.78 divided by 201 equals a V of 0.0134. And so we take that and multiply by 200, and we end up with 2.766. So this plus this equals this. That was the problem, is that because this number is so big, which is entirely my fault, the rounding error became a problem. And that's all there is to that. So I hadn't intended for this to take half an hour, but there we go. Now, only 2 of you are still watching, but thank you for spending some time with me. And 3 people to say dragon fruit to me in the morning at any point. I don't care. If you see me say it, we'll get an extra 5 points on the quiz. So I hope this was helpful, and I'll see you in class.